Last lesson, we fed a curve into a machine, and out came its slope, a rate of change at every point. Today we run that machine backward. We start with a rate, we add it up as it changes, and out comes the area under a curve. By the end, those two machines, the slope and the area, will turn out to be one machine, driven in opposite directions. Here is where we left off. This straight line is y equals 2x. Returning viewers will recognize it. 2x was the derivative of x squared, the slope function we built last time. A slope is a rate, so read this line as a rate, how fast a total is piling up. The total it is piling up is the area trapped underneath it, from 0 across to some point x. That shaded region is what we mean by the area under a curve. Our whole job is to measure it and to watch it grow. We have no formula for the area under a slanted line yet, so we approximate. Cover the region with rectangles of equal width, standing side by side. Each rectangle is easy. Its area is width times height, and the height is just the line, 2x, read at the rectangle's edge. Add the rectangle areas, and you get a first estimate of the total. With 4 rectangles out to x equals 2, that estimate is 5. But look at the tops. Each rectangle pokes a little above the line, so the estimate is too big. It overshoots the true area by those small corner triangles. Now anchor each rectangle at its left edge instead. They drop below the line and undershoot. That estimate is 3. So the true area is trapped between 3 and 5. Both estimates are chasing the same number. It is close already, and we have a knob we have not turned yet. The knob is the width. Make the rectangles thinner and pack in more of them. Watch the estimate as the width shrinks. 4 rectangles give 5, 8 give 4.5, 20 give 4.2. The gap between too big and too small is closing, one thin corner triangle at a time. Keep going, 4.04, then 4.004. The estimate settles onto 4 and stays there. And 4 we can check by hand, because the area under a straight line is just a triangle. Half of base times height, half of 2 times 4 is 4, exactly 4. No single rectangle pile was ever exact. Their limit is. That is lesson 1, doing quiet work. One area is a small prize. The real power is letting the total grow. Slide the right edge to the right, and the trapped area grows with it. Read the running total as it sweeps. This growing number is our accumulating total, the whole point of the video. At x equals 0 there is no area yet, so the total starts at 0. At x equals 1 the area is 1. At x equals 2, 4. At x equals 3, 9. Now do the thing lesson 2 taught us to love. Take each total and plot it as a height on a second graph. Those heights trace out a curve of their own. 1, 4, 9, sitting above 1, 2, 3, those are the squares. The running total is exactly x squared, and it should be, since half of x times 2x is x squared. So the area under 2x, collected up to x, is the function x squared. Now ask the lesson 2 question about this new curve. What is its slope? You already know the answer. The derivative of x squared is 2x. Watch the tangent slide along the area curve, and report its slope at each point. At x equals 1, slope 2. At x equals 2, slope 4. The slope reads 2x. Hold one point in mind. The height of the line at x equals 2 is 4. The slope of the parabola at x equals 2 is also 4. The same number from 2 different pictures. But 2x is the very line we started under. So the slope of the area curve is the height of the original curve, point for point. Piling up the height gives the area. The slope of that area gives the height back. 2 directions of one machine. This running total has a name. It is the integral. And a symbol, a tall stretched S, for some, because a pile of rectangles is all it ever was. We write the integral from 0 to x of 2t dt, and it equals x squared. Nothing here needed a straight line. Slide rectangles under any curve you like, narrow them, and the same running total builds. Area under a curve is a plain sentence now. Add up the height as you cross, and keep a running total. One honest footnote. Where a curve dips below the axis, that area counts as negative. It is the only asterisk, and it is for another day. And the pairing you just watched, slope one way, area the other, has a grand name. The fundamental theorem of calculus. You did not memorize it, you built it. 2 lessons ago this was 0 over 0. Now it adds up.